Hello. We're going to try a problem involving simple harmonic motion involving a mass spring system, as you can see right here. Okay. Um, Now to save time, I've actually went ahead and wrote down all the given. I will go over them, the goals and the formulas, because this one, it's a very typical physics problem where there's a lot of goals, but it's breaking down really easy, and I think it's a really good problem to start. So let's go ahead and look at it. You're given the mass. I went ahead and converted the kilograms into significant figures. The spring constant, which should be known as the elastic constant, because not all elastic substances are springs, rubber to be exact. And at t equals 0, the initial displacement, or which will end up being the amplitude really of the simple harmonic motion, is 0.11 meters, starts from rest on a frictionless surface, which means there is no dampening. Okay? I'll make a note there in red. There we go. No damping. Okay? And we have a plethora of things we're going to solve for. Angular frequency, frequency itself and the period, amplitude of the displacement and the position, amplitude of the velocity and acceleration. These should not be the same thing. And also the phase constant. One thing that I actually left out is there should be an F here, which is it's asking for the displacement function. So I went ahead and included that as well. Honestly, that's once you do everything from A to E, everything kind of falls into place. Now, formulas are very important. Now, I recommend actually solving it in the order where it has, starting with the angular frequency. Now, for a mass spring system, the angular frequency is the square root of k over m. So we're given that and that, so good to go. And then from there, we can solve for frequency, and then the period is just the inverse of that. Okay? And then we'll need these three formulas, which essentially describe the kinematics of simple harmonic motion. And take note that this is first derivative of, when you take the first derivative of the position, you get the velocity, and you take the second derivative of that, then you get the acceleration. And you can also take the integrals of those as well, not F. Okay, actually let me just erase those. Okay, and that should give us enough to get started. So I have already the calculations in front of me, so I'm going to go ahead and skip over that. I'm just going to go ahead and write the solution as the best way as I can explain. Okay, so you can pause along as whatever you wish. Starting off with angular frequency. Okay, it's just simply k over m. Make sure your units are already in terms of metric units, newtons and meters. So this one is already given to us in SI units. And the mass, there you go. Okay. And just a little sidestep, what I usually like to do with the units. I have the square root of kilogram meters per second squared over meters. That should extend over there for kilogram. So the kilograms cancel out, the meters cancel out. Okay, and then what we have left behind is square root of 1 over second squared. Okay, and you end up with a numerical answer of 9.78 but when we take the square root of the units, that's 1 over second square, 1 over seconds rather. But since it's angular frequency, we're going to go ahead and add rad, because rad is actually unitless. So it's almost like a ghost unit, but it is there. We're talking about angular frequency. It's almost like an angular velocity too. Okay? And that's just the first part of it. And then we have to solve for the frequency. Angular frequency is also that. Some simple algebra there. Just divide 9.78 per second divided by 2 pi, and essentially the 2 pi's also has units of rad as well, so that cancels out. So we're going to end up with a unit of 1 over second, which actually is hertz. Okay, giving us approximately 1.6 hertz. Approximately. Okay, and then the period is just simply the 1 over that. So it's 1 over 1.6, and hertz, remember, is 1 over second. So we're going to actually end up with a unit of time, seconds, and boom, 0.64. Now the book said it's around 640 milliseconds. Either one should be fine. Okay. Boom. Okay. Cool. Now I'm going to make some room. B is actually pretty much straightforward. If we have a frictionless system where there is no loss of kinetic energy and potential energy due to thermal energy, then the amplitude is just simply boom, that. So that's almost straightforward. Okay. Oops, not red, not red. And let me go back to these formulas. Let me erase all that stuff. Now, what I should say here is that this is actually the amplitude of our velocity wave, and this is our amplitude of our acceleration. So that pretty much gives us our parts C and D. That Vm is just okay, so that's 9.78 per second times 0.11. This almost gives us the wave speed. Now take note, radians is a really weird unit because radians can actually just equal to a ratio of units. It's almost just equal to meter over meter. I'll explain that some other time. So that should just be equal to 1. Okay? So I have to get my calculator a little bit. And you're going to get amplitude of the velocity of about 1.1 meters. It's actually 1.0758. But remember, we're only looking for 2 significant figures. Amplitude. Okay, amplitude is actually the square of the angular frequency, still times that. So it's going to be 9.78. I'm still going to write it as 1 over s squared times 0. Okay. And sure enough, it gets us 10.5 something, but round off the two significant figures, it's 11. And meters per second squared. Okay, so we're going to continue this problem. I'm going to solve parts E and F here on the bottom page. Okay, so now just to remind you, we're looking for the phase constant. Okay, so how do we solve for the phase constant? Now we're going to use something, borrowing once again from calculus, something called initial conditions. Now you may be familiar with this technique. Okay, and just to remind you, at t equals 0, said it started at 0, but something else, that the x position was 11 centimeters. But remember, this is actually our amplitude of our displacement. Okay, so I'm going to actually write the traditional simple harmonic motion function right here. And that's phi. But at t equals 0, it's going to become, just substitute in 0, cosine, well, that's times 0, so that's going to go away. This is phi, goes to 0. But at time equals 0, this is equal to xm. Now check this out. I'll put the parentheses there even though I don't need it. And so I get, and I can actually add a 1 right there. If I divide both sides by xm, this is actually what the book did, cancels xm out, and you're left with 1 equals cosine of phi. Now if you go a step ahead, you can either ask yourself what angle gives you a cosine of 1, or you can do this, that phi is equal to, or we just do it the other way around, arc cosine of 1 equals phi, and I'll just write it over here. The answer is that it could be 0 radians degrees, well, this is going to be radians, plus 2 pi n, where n is actually a counting number. Okay, we're just going to use the most simplest case. Simplicity is key, where phi is 0. Okay, 0 radians. And so the last but not the least is just to write out the displacement function. We already have our velocity, or at least the amplitude of that. And I'm going to take this same function that I wrote earlier and just spell it out. Simple harmonic motion. So now that we know every part of it, we'll just plug and chug. Amplitude, cosine, plus 0, and the units of all of this should be in terms of meters. So our final displacement function is just 0. Cosine 78t. This is in terms of meters. And there we go. So hopefully you're able to bring all of this together from A, B, C, D, F, and just take note that what it is, it's just one case of simple harmonic motion, and you're just describing all of the steps. Okay? So please take a look at it, try it out yourself, and hopefully enjoy.